Welcome to qnawire.
The energy of the spin-orbit coupling is given by mu z times b. Mu z is the magnetic momentum for an electron, and considering the spin interaction, we have minus g mu b ms, and this is multiplied by b. So the difference between these energies is because of this contribution to the energy. So we have EA minus EB being equal to minus G mu B times B times MS A minus MS B. Then we can solve for B to get B is equal to EA minus EB divided by G times mu B times MSA minus MSB. Now we can plug in the values that are given by the problem to solve for B. B is equals to EA minus EB, which is 5 times 10 to minus 5 electron volts. We will multiply it by the electron charge to convert it from electron volts to joules. So by multiplying it by 1.6 times 10 to the minus 19, we are converting it. And it is divided by 2.0023, forgot this minus sign on here, times mu b, which is 9.27 times 10 to minus 24, times, now, what are the values of MSB and MSB? Well, note that in the first case here we have J equals to 3/2, and in the second case we have J equals to 1/2. Remembering that J is equals to L plus or minus S, we can conclude that L is equals to 1 and MS can be either equals to plus 1/2 or minus 1/2 as always. Then one of the S is equals to 1/2 and another one is equals to minus 1/2. In this case we have S equals to 1/2, so MSA is equals to 1/2. In the second case we have S equals to minus 1/2, so we have minus 1/2 for MSB. We can simplify this by noting that minus 5 minus 19 is minus 24, so these three terms simplifies out, and here we have 1/2 minus minus 1/2, which is just 1. Then we get B as being equals to 5 times 1.6 divided by minus 2.0023 times 9.27, and this is approximately minus 0.4 Teslas. But we ignore the minus signal as we want to determine only the intensity of the magnetic field. If we consider the nucleus to be a current loop of radius r that is revolving around the electron, we get that the magnetic field produced at the center of the current loop is given by B equals to mu 0 times I divided by 2 times r, where r is the radius of that current loop. Then we have to model the current. The current is equals to the variation of the charge divided by the time. What we have here is the charge of the nucleus, which is given by E, divided by the period of rotation. And then this is equals to E times the inverse period is just the frequency of rotation. And the frequency of rotation for a charge undergoing a circular motion is given by V divided by 2 pi times the radius of rotation. Now we can multiply both the numerator and the denominator by the mass of the electron times the radius to get E times M times ME times R times V divided by 2 pi times me times r squared. We note that this is equals to LE. So this is the angular momentum of that charge. So the current is then equals to E times L divided by 2 pi me r squared. Therefore, the magnetic field is given by mu0 times E times L divided by 2 pi times me times r to the third. Note the following. L is equals to h bar times the square root of L times L plus 1. As we have already seen, in this case, for our atom in our particular state, L is equals to 1, then L is equals to h bar times the square root of 2. Therefore, the magnetic field is given by mu0 times E times h bar times the square root of 2 divided by 2 pi times me times r to the third. Now for the radials, you can look at figure 9b of the book, which is presented here. Then we can see that the most probable radius is r equals to 4 times r0. Therefore, the magnetic field is given by mu0 times E times h bar square root of 2 divided by 2 pi me times 4 to the third times r0 to the third. Then we can start to substitute the values of the constant to get the magnetic field. But first note that E times h bar divided by 2 times me is equals to mu b. Therefore, the magnetic field B is equals to mu0 times mu b times the square root of 2 divided by 2 pi times 4 to the third times r0 to the third. Then we can plug in the values of the constants to get the magnetic field. B is equals to mu0, which is 4 pi times 10 to the minus 7 times mu b, which is 9.27 times 10 to minus 24 times the square root of 2 divided by 2 pi times 4 to the third times 0.529 times 10 to minus 10 to the third. And this gives us a magnetic field of approximately 0.5 Teslas.